Now, the fourth factor that influences the way hemoglobin behaves is called 2,3-DPG, aka 2,3-BPG. So you may see this in different literature in different ways, but just understand it's the same thing. 2,3-diphosphoglycerate or biphosphoglycerate, is referring to the same molecule. So this is produced in red blood cells under conditions of anemia or low oxygen saturation. This is also produced at high altitudes, which also equals low oxygen saturation. And so basically under these types of states, we create more of this 2,3-DPG. And the way that 2,3-DPG acts is by blocking the interaction of hemoglobin and oxygen. Okay, so it's going to basically kind of block hemoglobin from wanting to attract or to bind oxygen. And it's synthesized in response to anemia. So that makes sense, right? If you think about that. Under instances or situations of anemia or low oxygen, I don't want hemoglobin to be bound very tightly to oxygen. Again, I want it to dissociate off very easily. I want it to enhance the way that oxygen unloads from hemoglobin. And this is why 2,3-DPG is created under instances of anemia or high altitude where we have low partial pressures of oxygen, okay? And then we also want to talk about, so let's look at this curve here. So we're seeing oxygen saturation in the absence of 2,3-DPG and oxygen saturation with 2,3-BPG present. And all we're seeing here is a shift to the right, meaning that we need a higher partial pressure of oxygen in order to fully saturate hemoglobin, because hemoglobin doesn't want to bind easily to, doesn't want to bind that oxygen easily, okay? At the bottom here, we're going to mention carbon monoxide. Again, we talked about carbon monoxide a little bit in chapter 15, and it's basically this alternate molecule that has an ability to bind onto hemoglobin, and because it does so irreversibly, and it also does so at higher affinities, meaning that it's more attracted to hemoglobin than oxygen is, what we see is that it prevents oxygen from binding onto those heme spots. So it competes with oxygen molecules for those heme spots. And as we can see, this can become fatal, right? If we can't bind oxygen because carbon monoxide is kind of in the way, then we cannot circulate oxygen, we cannot oxygenate tissues. Okay, now we'll speak a little bit about the role of carbon dioxide, the way carbon dioxide is transported. And this brings us to speak about carbonic anhydrase. And this is something we also introduced in chapter 15. So carbonic anhydrase catalyzes the reaction of carbon dioxide plus water to form carbonic acid. And that is really how we circulate the majority of our carbon dioxide. So carbon dioxide exchange we know happens in the systemic tissues. What direction is it moving in systemic tissues at the capillary beds? So is it going from tissue to capillary or capillary to tissue? Tissue to capillary, right? And in the pulmonary circulation, it's going from capillary to alveoli, right? To be exhaled. And the way that oxygen influences this is that in the presence of CO2, oxygen again shifts to the right and unloads very easily from carbon monoxide, from hemoglobin. Okay, so in this table, we're comparing the three mechanisms for circulating carbon dioxide. It can be dissolved in the blood to a lesser extent. It can be circulated as bicarbonate, and this is the reaction that is catalyzed by carbonic anhydrase, or it can be bound to hemoglobin, as we saw, again, to a lesser extent. And so what I really want to point out here is that there is more CO2 dissolved in our blood. Remember, we talked about only 1.5% of oxygen being circulated in the blood. Here we've got 5.5% of CO2 circulated. But a lot of, the majority rather, of that CO2 is bound, is circulating via that carbonic anhydrase mechanism. So this is the majority of our CO2 circulating through that carbonic anhydrase mechanism. And to a lesser extent, we can have it freely dissolved or we can have it bound to hemoglobin. And so this is that reaction. So we've got CO2 plus water catalyzed by carbonic anhydrase to give us carbonic acid. So this is carbonic acid. And that can freely dissociate to protons and bicarbonate, okay? And those protons and bicarbonate is what moves around in the blood, and then they are catalyzed in the reverse direction when they need to be exhaled at the level of the lungs. And so again, if we're looking at the law of mass action here, increase in CO2 levels drive this reaction towards our products, bicarb and protons, hydrogen ions, and then increase in protons or hydrogen ions and bicarb drives the reaction in the reverse direction towards the production of CO2 in the lungs so that CO2 can be expired. Okay, so really important to understand here that depending on where we are in the body, what tissues we're at, this reaction is being driven in the right or driven to the left in order to make bicarb and hydrogen ions or to make CO2 and water to be exhaled in the lungs. Okay. All right. Now this graph is comparing the total amount of CO2 against the partial pressure of CO2 and the way it behaves differently for different amounts of oxygen. So at a oxygen saturation of 0, right, we've got no oxygen in the blood, to a partial pressure of 100, right, which is what our systemic arteries look like, we can see that the amount of CO2 in the blood differs, okay, for the same partial pressure. So if we have no oxygen present, then we've got lots of CO2 circulating in the blood. And if we've got lots of oxygen present, then we've got little CO2 circulating in the blood. So this is really showing us that oxygen influences how much CO2 is circulating or mobilizing in the blood. And this is looking at all three of those mechanisms we talked about, right? Bound to hemoglobin, freely dissolved, and using that carbonic anhydrase mechanism. So using all three of those mechanisms, we can transport less CO2 if we've got more oxygen, and we transport more CO2 if we've got less oxygen.